So we are building up your intuition for rotation. So now we're going to build it up one more way. Who thinks they can balance this comically oversized lecture pointer on their hand without letting it fall over? If you think you can do that, come down here. I want to see you do it. Surely one of you believes you can do this. Do we have any jugglers? Any potential circus people here? I was either physics or I was going to join. Oh, yeah, come on down. Yes. Let's see. Potential circus workers. Okay, so take this and put the heavy part. I would suggest your whole hand, not your finger. Depends on how wild you feel. And see if you can balance that. Oh, shit. Don't let it fall on the people. Okay. Okay. So you balanced it. Wait, hold on. You balanced it for, we already know this guy, Hansen, and I don't have any more Hansen burns, so it's okay. Now, do it with that. Do it with a piece of chalk. Oh, you're terrible at it. Try again. Right. Chalk is shorter. Oh, my God. Can't do chalk. So why can he do this? So that's good, thanks. Why can he do this and he can't do chalk? Right? Because we have no intuition for rotational motion. You'd think the chalk would be easy, but it isn't. Oh, no. Okay. Sorry. No one has ever been injured in any of my classes. Ever. It's never happened. Okay. Except me. But you only die once, so you know it's always worth it. Okay, so here's the reason. Let's think about the angular acceleration of what's really going on here. We have a really long lecture pointer here, and its length is L. And now let's say you're trying to balance it. What happens? It invariably starts to tip over. Okay, so you got your hand here. You got your lecture pointer here, like this. It starts to tip over. So let's think about the forces. We say, well, some of the torques is I alpha. I took this fun activity and I'm turning into a nightmare. Some of the torques is I alpha. We want to think about torque and moment. So what do we need? An axis of rotation. Yes. I would put it here where the thing's actually going to rotate. So we're going to put the axis there. We want to think about this thing rotating off of your hand. So therefore, what is the torque? Well, we have a force mg down. We have a normal force up from your hand, basically. Well, the good news is, if we put the axis of rotation there, we don't have to think about the normal force. Right? It gets canceled out, or the r vector is 0. But this one, okay, there's the r vector. Put your chalk on the axis of rotation and go here. And mg is down, right? And say it falls to some angle theta. Then the torque, due to that, is L over 2, right? That's the value of r. The force is mg, and its component in this direction is sine theta. We don't need to do the trig again. Go back to last week. So there you go. It's like that. So that's the torque. Okay. Now, what is the moment of inertia of a rod from the edge? Oh, we're supposed to do the calculus part of the lecture to know that. I forgot. Hold on. It's 1/3 ml squared. Okay. In the center, your formula sheet said it was 1/12 ml squared. That's because that's if you rotate it here. We're rotating on the end. So maybe you can imagine rotating a rod from the end is a bigger moment than in the center. Just rotate something heavy, and you'll convince yourself of that. Somebody asks, why is the normal force canceled out? It's not canceled out. We could add it in. So the torque from the normal force is the r value, the distance, 0, times the force, n, times the sine of theta. It's because it has no distance from the axis to where the force is applied. So it's not 0. It's not canceled. It's just 0. It applies. That's why I chose that axis. What does the mean? This is the axis of rotation, if that's what you're talking about. My x's sometimes mean axis of rotation. Why do we know it's exactly 1/3? Don't make me do calculus. Okay. So we could do an integral, and we might do that if we have time. If you're dying to see it, we can do it in office hours. But just the integral version of getting the moment of inertia tells you it's 1/3. Okay, what are we doing here? So we have all this junk equals, right, so there's I, there's the torques. But now we have to think about sort of the biological human element of this. What determines whether or not you can balance this or not? It's kind of like your reaction time, right? It starts to fall over, and my brain says, oh, we got to get under it. We got to get under it here. Oh, my God, right? So I have a certain reaction time. When I'm that spastic, it's maybe, 100 milliseconds or something. So you got to be able to get under it. when it starts to fall. So if you want to be able to balance it, you need alpha to be small. Yeah, you need alpha to be small, right? If it falls slowly, you can get back under it. If it falls fast, you can't get back under it, right? So let's look at how alpha scales. So then we have alpha equals, I'm going to roll this out, L over 2 mg sine theta over 1/3 ml squared, right? Doesn't depend on the mass. What do you get over here? You get 3 over 2, and one of the L's goes away. 3 over 2 sine theta over L. So the angular acceleration is inverse to the length. Oh, right. So if something's long, if L is big, this goes really slow. And if this goes really slow, it's easy to get under it before it falls. If L is really small, the angular acceleration is so fast that I can't get under it. Right? And neither could he. It's okay. Nobody can do it. Well, some Cirque du Soleil person can probably do it, but most people can't do it. Okay? So there's your intuition. Now, do you believe that? See, here's what I love about the universe. Is you always think you understand something, and it's like, no, it's more complicated than that, especially in biology. Here's some good questions about how to do problems. Why is it L over 2? Because remember, this vector is from the point the force is applied, or the axis of rotation to where the force is applied, and the weight is applied at the center of mass, and for a uniform rod, the center of mass is in the middle. So the length of that vector is L over 2. The rod is L, which I didn't tell you. Okay. Where did the G go? I don't know. I left it out. There you go. Here, I'll put it in this just to make it nicer for you. There we go. It's orange. Where did the 1/3 come from? That is the moment of a rod from the edge. Anyway, so what I was getting to is telling you that it may not be this simple. Because I've said, oh, well, your brain just has to watch how far it's accelerating. How big is the angular acceleration and get back under it, right? Okay, well, watch this. Right? You can do it with your eyes closed, right? I don't need to see the angular acceleration. But this, eyes closed doesn't help. Right? So it doesn't matter. So it's not just that you can see the angular acceleration. I think it's also that this is heavier, and you can actually feel it tilt over. So it does have to do with alpha, but I think it's more how the forces are being applied to your hand. As it falls this way, I can kind of feel that with my hand, and it falls this way, I can kind of feel that with my hand. Right? So some bioscience people can tell me if this is actually important, or some kinesiology people. Because I don't know anything about biology.